This is another pulley system that has two chords in it. The first chord is this green line, and the second chord is this light blue line. So what this problem is asking, it's telling us that A, this point A right here, is being pulled down at 2 meters per second. A is being pulled down like this. So like we do with all our pulley systems, we have to reference it from a fixed point. This is a good point right here. This pulley is supported by this structure, and we're interested at point A right here. So this will be positive direction going down. It will be SA. This point right here, how should I do this? This point going through right here will be SB, how far down this block B is. And this pulley right here, which also changes position when the system moves, we'll call this SC. And for all these, down is the positive position as shown by the arrow. And in our analysis, like we always do, we are going to ignore the parts of the pulley that do not change position with respect to time, and that's all of the pulley that's over the all of the parts of the cord that is over the pulley, and this part of the cord. Now we can go through and we can write our equation. Starting with cord 1, we trace the entire cord, and we get a length of SA minus SC. So SA minus SC, this length right here, and then we have another plus SB minus SC, plus SB minus SC, and that's this length right here. And when we trace the pulley up over here, we have a length of SB plus SB, and this is equal to L1. So this is cord 1. And we can simplify this equation up a bit. We get SA plus 2SB minus 2SC is equal to L1. And when we differentiate with respect to time to get the velocity, we get a VA plus 2VB minus 2VC is equal to 0. We get a 0 because L1 is a constant and the derivative of a constant is 0. So this is our first equation right here. And in this equation, in this problem, we are given that A is being pulled down 2 meters per second. So the velocity of A is equal to 2 meters per second. And because it's moving down, it's moving in the same way as our positive distance. So it's a positive 2 meters per second. And we want to find out what VB is. So VB is sort of what we're looking for. And if you look at this equation, we know what VA is, and we have two other unknowns. So we're going to have to figure out a way to determine one of these unknowns. And because we have two chords, we can look at the second chord, cord 2, and maybe this will give us some information that we need. So cord 2 is this blue line, and if we trace this from one end to the other, we get a chord length of SC. Plus is constant plus SB. And this is equal to another length, L2. So if we differentiate this with respect to time to get our velocities, we get VC plus VB is equal to 0. And right here we get VC is equal to negative VB. And this is our second equation. So what can we do? Well, we have a term for VC, we have an expression for VC, so we can plug equation 2 into equation 1. And we get VA plus 2VB minus 2 times VC, and we're going to substitute our expression for VC, so VC is equal to minus VB, and this is equal to 0. And when we simplify this equation up, we get VA plus 4 VB is equal to 0. And we get 4 because this minus sign times this minus sign is equal to a plus, and we add these VB's together. So we get, if we solve for VB, we get VB is equal to minus VA over 4. And this is equal to 2, so minus 2 over 4. And this is equal to 1/2. So this pulley, the velocity of B right here is moving, it's negative, so it's moving up at 1/2 meters per second. And we know it's a negative sign and it's moving up because it is opposing our positive convention. So VB is equal to 1/2 meters per second in the upwards direction.